What's up, everyone? Welcome back. So as you guys notice, my voice is still not fully recovered yet, but well, because again, I caught a cold a couple days ago, and it's getting better, but yeah, I still I'm still a little bit sick. But anyway, so we're going to continue working on the inequalities. Yeah, again, we're going to solve the inequalities of polynomials, and this is part 2 of it. So if you didn't watch part 1 yet, go to the link. Go to the description. I'll put the link below. Watch that first, so that you see the 2 examples. Now, for today's video, we're going to look at a more general way to solve it, and we're going to look at the actual trick. Well, actually, there will be 2 different tricks that we can use to solve inequalities of polynomials in general. So here we go. So first, let's look at the general case number 1, which is still not the most general form of it. So here we are going to say that now we have a polynomial that we already factorized, so that we know the roots of the polynomial if it is an equation. And the setup that we have would be x minus the roots a1 times x minus the roots a2 times ... all the way to x minus an. So we see that in this case there are 2 different two things in our setup. First, we have exactly n different roots. So we have a1, a2, all the way up to an. Next, we also can see that in this expression of the polynomial, each root is what we call a simple root. So what it means is that it has only the first power for each root. So we don't see any exponents for each factor, meaning that there's only one copy of it. Then after that, we of course have the inequality sign, and then a 0 on the right hand side already. Okay, so of course, most of the time when we see the problem, we probably don't have the 0 on the right hand side. So what we have to do is, of course, we need to move the 0, well, move everything on the right hand side to the left, and then we're going to factorize it so that we'll get something like this. And perhaps you might actually see a negative sign at the end on the left hand side, because again, it's possible that the leading coefficient is negative. In that case, we of course just need to divide both sides by -1. And don't forget something very basic in inequality sign, that when we divide both sides by a negative number or multiply by a negative number, we always need to flip the sign, flip the inequality sign. Okay, so such as if we have less than or equal to, right here, if we multiply both sides by -1, or again divide by, we will flip it, and then it turns into greater than or equal to. Again, greater than or equal to. Similarly, if we have something such as greater than at the beginning, then after we divide both sides by -1, we need to change it into less than. Okay. Now there's one more inequality sign that most people usually don't don't use that often, especially when we solve inequalities, which is the not equal sign. Well, what does it really mean for not equal? In fact, it just really means that it is less than or greater than at the same time, as long as it's not equal. So when we flip this sign by multiplying -1 or divide by -1, we just need to flip both signs at the same time, meaning that now the less than part will turn into greater than, and then the greater than sign will turn into less than. But if we combine these two back together, we still have less than or greater than. So that we will still end up with the same unequal sign, okay? So anyway, this is something about doing inequalities when we need to pay attention to the sign, but we will find another time to talk about it. So when we get to this setup here, now we will just think of the trick, okay? So suppose that the answers or the roots are going in an increasing order. So we have A1 is less than A2, less than A3, all the way until this, okay? Then the trick is the following. We can actually claim the result already based on the trick, which is now if n is even, then we will get this. We can always claim that based off what we have here, we can always claim the following. Which is x is either between A1 to A2, or x is between A3 to A4, or all the way the x is between an-1 to an. And if n is an odd number, in other words, if there are actually odd number of factors in our expression, we will get this. We now will get x is less than A1, and then, or x is between A2 and A3, and all the way to this. Okay, so here this part works for less than or equal sign. How do we know that? So here is where the trick comes from. We of course need to do something a little bit extra in this trick, which is we need to look at the graph of the polynomial. So the important thing here is, if we think of the polynomial itself, no matter what the roots are, we know that there is a general shape of a polynomial, such as if there is only one factor, we know that it's a linear function, which is just a straight line like this. Let me use a red pen. Like this. If there are two factors, we of course will get a parabola like this. Now, what if we have a higher degree polynomial, such as if it is a cube, it will look something like this. If it is a quartic polynomial, meaning that it's a degree 4, it will go and with 4 roots, it will turn something like this, with 4 different points hitting the x-axis. So degree 5, it will pass 5 times, so on and so forth. based on our setup here. So how is this going to help us? Well, one thing that we can notice is that when we have an even degree polynomial, we see that the graph will always ending up like this, meaning that the two ends are always pointing upward, no matter how they change in the middle. When we push the graph far enough, we will see that both ends are pointing upward. We call it approaching to positive infinity, meaning that the y value is getting bigger and bigger in positive direction. Where the odd functions will also have something similar. We still see that as x getting bigger and bigger, the y value is also getting bigger, approaching to positive infinity. However, when x is getting smaller and smaller, meaning that when it's going to the left or the negative direction, the y value is also getting smaller and smaller, meaning that it's going to the negative infinity direction, like this. So if we already remember this, then we can always remember how the graph would change in the middle, such that we can always see that if there's only one copy of each factor in that polynomial, we can generalize the answer by the following. We see that for the even case, we'll start off with something that's positive here, and then after the first time it will turn into negative, positive, negative, and then positive again. They're always going back and forth. Good. That's why we can claim the following. If we want to take something that is less than, then we will just count which region we want, and seeing that it will start from positive, negative, positive, negative, positive, negative. So the most right region will always end up with positive. And we can, starting from the most right and then count backwardly to see that which regions we want as our solution. Similarly, for the odd functions, we can do the same thing. Let me use this. So for the odd functions, we can also do the regions like this. So we have positive on the most right, and then the one right before it will be negative, and then the one right before it will then positive, and then it will end up with negative at the end, like this. So since we have positive on the most right no matter what function we have, we can also count it from the most right and go backwardly to see which regions we want, and we just take every other region after we write it. So good. Now if we change it to greater than, we'll just do the same thing again, starting from the most right, and then see if we keep that region or we don't need that, and then we'll just move on to the next one, and so on and so forth. We'll be able to generalize our solution, no matter what the roots are. Of course, one more thing is that we need to know the order of the roots in an increasing order. So when we write the answer, we need to make sure that the order is rearranged into an increasing order before we put it down. So that is the first trick for solving an inequality of polynomial. If we have a nice setup that each polynomial, well, not each factor is only in degree 1. In other words, there's only one copy for each factor. Good. So next, we're going to look at the more generalized expression, meaning that what if some of them are not in one not in degree 1 anymore, or not with more than one copy. What can we do then? All right. Okay, so now we finally have a most general form, which is the factors with possibly more than one copy. So the k1, k2, all the way up to kn are just positive integers that represents how many copies of each factor we will probably have. So now if we have more than one copy, what do we need to be aware of in solving such inequalities? So now we need to go back and use the kind of the same method as we did in part 1 of this video. That it's better to make a table. But first, again, we need to assume the order of those roots are in an increasing order already. So I'm not going to write here again. We just assume that those are already in an increasing order. Otherwise, we need to rearrange it such that the first factor will have the roots that has the smallest value. Okay, let's say if this like we have one negative value and the rest are just positive, then we'll put the negative value in at the beginning. Then the next smallest will in the second term, so on and so forth. So with the setup, we're now going to make the charts again. Let me use this pen. So again, we're going to make an X here. And then down here, we'll just call it f of x. Or again, if you like to use the word y, go ahead. It's all up to you. It doesn't really matter. It's just telling us that the second row is just the image, or most people will just think as the output of whatever the expressions is. Okay. So again, we need to list all of the roots out. So we will have something like this: A1, A2, and then, well, here I'll just skip this part. So here I'll make a cross here because I need to break it into two parts. As we just generalize it, it depends how many ends we have. So I'll list the last two terms out as well, like this. So when we know how many roots we have, of course we need to list all of them out. Let's say if n is 10, then we need to put 10 those 10 values, and then we need to give 11 more squares in right next to them to get our full table. Anyway, good. We have something like this now. What should we do? Well, we already know that those values that we put are the roots. So for sure, that's the outputs, or the image of each a, k will be 0. So this is the first part of the table. Good. But remember, we're now doing inequality, not just equal. We are not only trying to find where those points are equal to 0. We also want to know what happened with other points that are not 0, whether they're positive or negative. Okay? So here is the problem. If we try to look at the graph, it will always change now, and the shape is varied because we now have exponents in the factor of those roots. And what do those exponents do to each factor? Here is the idea. It is actually an idea that need to use calculus, but here I'm not going to talk about something too deep related to calculus, but just bear with me. Here is what we have. Suppose we know that This point is A1, okay, for this graph here. So we say that in the last example, we have all the exponents equal to 1. So when the exponents are equal to 1, we see that they're always going straight line. So if it is starting from positive, it will go down as negative after passing through the point, like this, for k1 equals 1. Now, what if k1 is something not equal to 1? Again, we're now trying to generalize it. So if k1 is something bigger, such as k1 is equal to 2, for instance, remember those k values are positive integers. So don't ask what if it's 1.5. No, don't do that. So if k1 is equal to 2, the graph will actually end up with something like this. Now, as you can see that even for k1 equals 1 case, I didn't graph the whole function, and there is a reason why I'll do that. It's because right now we are only looking the points that are around A1, meaning that we're trying to look at the graph locally around A1, or yeah, sometimes we call relatively in calculus, such as when we talk about the relative extrema. Sometimes people will call it the those relative extrema, the local extrema or local extrema, meaning that now instead of looking the whole graph of the function from negative infinity to positive infinity, everything, we're now just trying to focus on one small region, and I'm going to use something like this. And again, this is, you can also connect this with something even some higher math called analysis, or to be precise, you can connect it with real analysis. And what we're doing is we're now making a very small region, and we're only looking around that small region instead of looking something very big or generally. Okay, sometimes when you call it looking at general graph, we can also call it globally, just like how we think the whole thing as global. Good. So now if we look at a small region like this, if of course how small, we call it arbitrary small, meaning that we can choose as small as you want. But if we do it this way, we will now see that when we're choosing a very, very small region that we want, if it is small enough, we will see that this function will it's not going to affect by other factors anymore. It will only be affected by the factor such that that factor is turning down to 0. Meaning that if we're looking around A1, we only need to look at this part, and this part is now telling us that k1 is equal to 2, meaning that now we have 2 copies of it, such that when we look just around here inside of the blue circle, we will actually get the shape of the function that looks very close to a parabola or a degree 2 polynomial. Okay, now what happens if we try to try to make it even higher? Let's say if k1 is equal to 3, or maybe k1 is equal to 3. So if k1 is equal to 3, we will now see that the graph is going to be like this. When k1 is equal to 3, the graph around A1 will really look like the cubic function, meaning that now we actually have a shape that looks very close to the degree 3 polynomial when it's just around here. Of course, if you move far enough, you will see that it's not going to be the same anymore. But if we are looking in a very small region, small enough to ignore other things, that part will actually give us a form that looks exactly well, I shouldn't say exactly, but nearly the same as the cubic function. So if we keep pushing it, we'll actually see two things. One, when we try to look at the shape of each roots locally, meaning that if we're putting a very small ball right here, a very small circle around it, then the shape of the graph inside of that small circle will actually have a shape that is pretty much the same as just the factor itself raised to that power, and it will just be the same as the polynomial of I should even say this way. It would just be the shape would just be the same as the shape of the power function based on k the k value we have. So for a1 here, we just need to look at the value of k1, and then we can tell that which power function it is, and we will get the same shape around a1. So let's say k1 is 5 as an exponent. Then we will know that the shape of this function around the small ball here will be the same as the shape of the power function x to the 5th power. Now if k is, let's say, 8, then the shape will just turn into again x to the 8th power, the power function. Good. So using this idea, we can just figure out each one quickly. Now, why does it help? Because now we're going to look at the second idea here. Since we now can tell the shape of the function around the those roots separately, then we know, and we also know the shape of each power function. We can now tell that based on the shape around each point, we can tell whether we'll get positive or negative before and after. For example, let's say k1 is an odd value, okay, an odd integer. We see that before a1 in this graph, we always have positive, and then right after it, it will turn into negative. However, if k1 is an even number, we see that no matter before or after, the a1 will end up with the y value that's positive. So what does that give us? It actually tells us that if k is odd, the sign will change. Of course, after passing through or after the roots. Now, if k is even, again, we just saw what happened here. Or we can just do one more example. Let's say if k1 is equal to 4, okay? Then we will get a quartic function like this. That's even flatter, but we still see that it's positive on the left-hand side and it's negative on the other side. It's even, then the sign remains the same. So you may ask, what if we start from negative? Well, same idea, because we know how the power functions look like. Let's say now I'm going to randomly pick another point. Let's say the endpoint, an. This is not working. So we know that it has to start from negative. So When it is far enough, it will look something like this. Let's say when kn is equal to 1, of course we know that it's linear, it will look like this, right? Now if kn is 2, then we'll get something like this. Just like an upside down parabola. So everything will just flip, but we also see that the properties down here in our conclusion does not change. We will still have the idea that if the exponent is even, the sign will still remain the same. If it starts from positive, it ends with positive. If it starts with negative, it will still end up with negative. And if the exponent is odd, we see that it has to change. So if it starts from negative, it will turn into positive. Or if we have the exponent is equal to 3, we'll have something like this, which is still the same. The sign will actually change after the roots. So here we cannot really generalize and claim that it's always positive or negative. Well, except the last one. But again, we have this property here so that to help us derive all the signs from the most right all the way back to the left, backwardly, so that even though we cannot immediately tell whether we should put positive or negative here, or anywhere, except the last one, after we make the table, we can use this idea to check the exponents so that we will be able to generalize it and get the sign for the regions in between quickly without actually solving the equation or the inequality. Good. So the last part of the video will be will just be an example of an inequality of polynomial that we now could just end up with, again, some exponents greater than 1, and see how we can use this to get us the answer quickly. And I'll pause this video right here. I'll see you guys in the next video for the last part.